Good morning. We are back looking at Chapter 2. In fact, we hope to finish up Chapter 2 today. We will finish up Chapter 2 today. We're looking at kinematics. We've looked at displacements. We've looked at velocities and accelerations. This is the last example we worked from, and I feel like we kind of finished that, so we'll move on from that. I just want to check with everybody and make sure that you're staying caught up in the course. I know I keep saying this all the time, but it's just so important to schedule and consistently spend time looking through the homework problems, looking through the lecture examples that we have in order to be successful in the course. So make sure that you're staying caught up. If there's any questions at all, stop by office hours. But let's go ahead and move on. Again, we're going to be looking at the remaining portions of Chapter 2 today. So this is the last example that we had looked at. It dealt with braking distance, and it was kind of interesting in that there was a section for a half second where the driver was responding, and during that time we used constant velocity to model what was going on. And then once the driver hits the brakes, then there was a braking period where things are going to be slowing down. And we assumed that the braking would consist of a constant acceleration. And from that, we were able to bring in, we did some graphs. So graphing was an important part of what we looked at that time. And then we carefully outlined what was going on in the graphs. And then we brought in our formulas for constant acceleration. And so, if they're not too far back, maybe that's something worth, there they are. So our formulas for constant acceleration, and I highlighted the ones that I feel like, 95% of the time, those are the ones that I'm going to. And so brought in the formulas, identified different quantities within those formulas, and then did the algebra. Okay, so the algebra, we got everything set up, carried out the algebra, and found out distances that were traveled using constant velocity and constant acceleration. So we did one after the other. And then stopping times. So I also took a look at stopping times. So it's a good example of certainly where we are. It's actually a good example of kind of all the stuff within the chapter. So let's try a couple of other examples here. This problem says that we've got two moving objects. We have a police car, and we have a driver who's speeding. And so the driver who is speeding passes the police car. And the idea here is, what would happen if, right as this speeder, who's going at constant speed, constant velocity, right at the time the speeder passes the police car takes off after it. Now, the police car is going to have to undergo an acceleration. So the police car's got to pick up speed in order to catch that speeder. And so the idea here then is, one way we could model this, let's look at a couple of graphs to see. What it would say is that the location of the speeder as a function of time is this straight line on the graph. And that means that the speeder is traveling at a constant velocity. So the speeder is just maintaining that same fast speed through this whole thing. Meanwhile, the police car is going to be undergoing an acceleration. So if we treat the acceleration as constant, and that's kind of the way we're going to model this, if the acceleration is constant, and then I went ahead and used the acceleration as 5.6 meters per second squared. I think they had left some information out on this one. So anyway, we've got the police car undergoing an acceleration. That's going to look like a parabola on our x versus t graph. And then the speeder is just going to look like a straight line. We want to see where the speeder and the police car meet. So at what point does the police car catch up with the speeder? Okay, and then the police car catches up, and at that point the police car is going faster, so it's going to pass the speeder. going to pull over, turn on the lights, start flashing, and have the speeder slow down. So here is how we're representing this. So the speeder just keeps going at a steady speed, kind of oblivious to these lights that are flashing in the rearview mirror. Meanwhile, the police car's speed is just catching up. Now notice, these graphs really aren't synchronized the right way. This graph is saying there's a time when the police car is traveling the same speed as the speeder. Is that going to work? Do you just have to reach the same speed and then you've caught up? And you go, no, it's not a question of operating at the same speed. In fact, we can go to the first graph. We can check the slope of the speeder. Now the slope here on the x versus t, that's a constant, steady, consistent slope. The police car reaches that speed right there. So kind of halfway through, maybe 7 or 8 seconds, the police car is already traveling as fast as the speeder. The problem is the speeder got a head start. So the police car has to go to an even higher speed to be able to catch up with the speeder. So the time scaling on this one doesn't match in the time scaling here. The time when they're traveling the same speed is kind of only halfway through that graph. Anyway, let's go ahead and take a look. What does it say? The speeding car is at 150 kilometers per hour. Let's take a look and see what's going on here. So here are the two cars. They're both moving. Here's V1, here's V2. Now, for car A traveling at V1, there's a constant acceleration, so apparently this is the police car. And for a constant acceleration, there's no initial velocity, right? And we can say that the position that they're starting from is 0. So that's going to give us some zeros. So I've got some zeros in those formulas. And what we can do then is we can simplify the expression so that there's no v naught term, there's no x naught term. The position or the location of the police car just becomes 1/2 a1 t squared. Now a1 I'm going to say is the acceleration of the police car, and that I inserted as 5.60 meters per second squared. The speed of the speeder is 150 kilometers per hour. So I did that trick of units conversion. The 150 kilometers is 150,000 meters. The hour is 3,600 seconds. And that gave me a speed of 41.7. So the speeder has a fixed speed given by this formula. And that says that while the police car has an acceleration term only, the speeder has constant velocity, so that's just going to be v2 times t. So two different formulas, one for acceleration, one for constant velocity. And what we want to say is happening is, at what point does x1 equal x2? And so what I'm going to do is take the x1 from here, representing the police car, and the x2 function, representing the speeder, and I'm going to set them equal to each other. Now what that should provide is a way to go in and solve for t. This is going to say, at what value of t will these displacements match? So I put in the acceleration and the velocities. I solved for t. I factored out 1t. There's kind of a trivial solution here. That solution would be that t is equal to 0. So at t equals 0, that's also a time when these two values match, but that's not the solution I want. So I want to look for the other solution, so I factored out the t's. And what was left gave me 2v2 over a1. That gave me a time of 14.9 seconds. Okay, so that's the time that it would take for them to catch up. Now what I can do then is I can solve for, I actually switched over and used distance. That's kind of interesting. Anyway, I'm using d instead of x2, I guess. I plugged in to find out what that distance would be. v2 times t, that's the speed, that's the amount of time I've calculated. And it says that the location where the police car catches up is 620 meters down the highway. Okay, so 620 meters there. And then, well, how fast is the police car going by the time they get there? And by the time they get there, the police car, if it continues to undergo an acceleration, is going 83 meters per second. 83 meters per second, that's like 170, 180 miles an hour. I don't think the police car wants to go that fast. So this is the way we modeled everything, but you can see we're running into some difficulties here. At some point, the police officer is really counting on the driver looking back and seeing those lights flashing and slowing down. So that's a more probable outcome for this problem. So here's, going back to this first page, I think what the police car is hoping is that at some point, when it begins to catch up, speeder sees the lights in the rearview mirror, and then they both slow down. And the police car, because you don't want to go 180 miles an hour out on the highway. The police car is going to go past, let's see, what's the other speed here? 150 kilometers per hour, which was, so these are some crazy numbers, well, a little crazy. So the speeder is going 80 miles an hour, right? So let's say this is roughly 80 miles an hour, something, maybe 90. So 90 miles an hour, and the police officer ends up going 180 miles an hour at the time when they catch up. Okay, anyway, so here's what it looks like. This looks like that first graph, and at 14.9 seconds they've caught up. But I guess I went in and corrected that second graph. I scaled it so that the times match, and pointed out that the velocity as a function of time, that one didn't get labeled. I need a time in seconds down here. That's going to reach the speed halfway through, but by the time the police officer catches up, it's going twice as fast as the speeder. That sounds really, really fast. Okay, so let's take a look at another set of examples. What we want to do is we want to look at the topic of freely falling objects. Now, the freely falling objects that's pretty useful, right? If we have something that's just dropping through the air, we want to be able to calculate how fast something is dropping. Now, what they've done with this apple is they've released it, and then they've taken a series of photos at a regular time interval. So they're showing that if we take pictures of where the apple is as a function of time, notice that at each one of these pictures, it's traveled a longer and longer distance compared with the previous intervals. So we can see that the delta x's are getting bigger when the delta t's are staying fixed. And so it's a higher velocity, right? When things are dropping in a gravitational field, they accelerate. Now, near the surface of the Earth, we can treat Earth's gravitation as almost a uniform gravitational field that creates a constant gravitational force, and that results in a constant gravitational acceleration. So near the surface of the Earth, all objects experience approximately the same acceleration due to gravity. Now, that means that we're not going to observe this effect if there's air resistance, right? If a leaf falls from a tree, it does not drop like a brick. So air resistance is going to be important. We have to make sure that the objects we're thinking about, for them, air resistance will be a small effect. Now, for almost any object, once it gets going fast enough, air resistance is going to become important, but we're going to neglect that for simplicity for right now. So this is one of the most common examples where we work with constant acceleration. To a good approximation, if you have a dense object, a fairly good-sized dense object, dropping in the gravitational field near the surface of the Earth, we can map that out pretty reliably. So here we go, freely falling objects, and as you can see, these pieces of paper, Kleenex, whatever, are not keeping up with the baseball. Is that what that is? And then over in this other example, we drop these. What they've done is, person has scrunched together the paper to minimize air resistance, and now it's actually keeping up. I don't know if that's going to happen exactly. But you can do these demonstrations. You can see these where if we pump air out of a container and then drop things within that container, within that room, things just drop. So you can see these demonstrations. You know, when astronauts went to the moon, one of the interesting demonstrations they did, I mean, you could have done this on Earth. You didn't have to go through the entire Apollo program to be able to get astronauts on the moon. But you can see these videos if you go online of astronauts dropping a hammer and a feather. And they just drop side by side on the moon. And on the moon, the gravitational field is 1/6 as large as the gravitational field on the surface of the Earth, and so it's happening more slowly. So it doesn't happen so fast. Earth's gravitational field is large enough, things drop pretty quickly. Okay, so here's a picture of that demonstration. And we actually have this. I don't have this demonstration with me here. So it's possible we have an air-filled tube. We drop the feather. We drop. We have some metal objects, some coins. But when you evacuate the air, when you take the air out, the feather drops like a brick. So let's see. What does that mean? That means if you didn't have an atmosphere, when the leaves fell off the trees, they would drop like bricks. You'd have to watch out for them. I guess they don't have a lot of mass to them if you got hit by one, but leaves falling off a tree could be hitting the ground at, if it's a tall tree, maybe they're hitting the ground at 100 miles an hour or something. So those leaves would really drop if there was no air resistance. Or think of raindrops. Now I know if there was no atmosphere, no pressure, then water wouldn't be in liquid form, but if you had a raindrop that somehow was able to drop through the air without air resistance, the raindrop would impact at hundreds of miles an hour. You'd have to get out of the way of the raindrops during the rainstorms. All right, so and here is the Tower of Pisa that Galileo is supposed to have done a series of experiments from. So here we are dropping something from the tower. Now, what they've done in this example, oh, here we go, right there. So they've designated the downwards direction as positive. And that makes sense. I mean, if we're dropping something, why not take the starting location and call that 0? And then as things move downwards, let's call that the positive direction, and that avoids the use of a lot of minus signs in the calculations. So what they're saying is, if you do these experiments, if you measure after 1 second, how far has the object dropped? And again, we want to get, I don't know, something dense and pretty good sized, maybe a metal sphere of something. So the air resistance effect is small. After 2 seconds, it's dropped 4 times as far, and after 3 seconds, it's dropped 9 times as far. Well, that's consistent with constant acceleration. Remember, our formulas for constant acceleration say that as time goes on, the displacement increases like 1/2 a t squared. So what this is saying is we're going to drop this, so the initial velocity is 0, from a tower 70 meters high. How far will it have fallen after 1, 2, and 3 seconds? They've kind of given the answers here. Here is the graph of what everything is going to look like. Let's take a look at the formulas and see how they came up with these numbers. So here's what my solution, my drawing looks like when I'm solving this problem. So I'm going to bring in my displacement formula. Now you'll notice they've switched over and they're using y. as the variable. So, you know, if x is horizontal, y, maybe that's vertical, but there's also no reason in a one-dimensional problem that we couldn't just use x for vertical directions too. Now, I know this sounds crazy, but I find that if I'm working in terms of x, I'm more reliable with my calculations than if I use y. Anyway, I'm gonna go ahead and use x. So I'm gonna say x equals 0, x naught is equal to 0. So x equals 0 is right at the top, and that becomes my x naught. That drops out. We're dropping this, which means we're letting go, which means the initial velocity is 0. So I get to drop out, the x naught term drops out, the v naught term drops out. So those two terms both drop out. The only thing I'm left with, and there it is, there's my simplification. The only thing I'm left with is the 1/2 a t squared term in the expression. That's the only thing left. So again, it's from rest, and I've decided on a coordinate system that I think is going to make the problem really as simple as possible. So now the acceleration that we measure for Earth's gravitational field near the surface of the Earth is 9.80, I'm going to say. It varies from location to location. But for the most part, we'll be using a number 9.80 meters per second squared. So you'll notice in the textbook, I think they have different locations listed in a table. And I think they actually list the Bay Area as being 9.8 for whatever reason. Anyway, 9.80 is what I'm going to be working from. So that's the acceleration, and that's going to get plugged into these formulas, which I'm going to use to come up with v and with x. Now my x formula is here. My v formula, I didn't write it here, but I still got it over here. The v naught is 0. So I'm plugging numbers into those formulas, and it's predicting what the velocities will be for 1 second, or 2 seconds, or 3 seconds after the drop. And then the displacement, how far will it have dropped? Those are the numbers that they gave us on that front, on the previous slide. On the previous slide, back. Oh, it is here, sorry, I went past it. Found the tower. So after 1 second, 4.9, 2 seconds, 19.6, 3, and it all comes from these formulas. So what's going on here? I mean, we've got the formulas figured out for constant acceleration. We're suggesting gravitation works in a manner where we would expect constant acceleration. So when we run these experiments, we find that we are able to predict them very well, very reliably, using the formulas of constant acceleration. Okay, when air resistance becomes an issue, then we have to add those extra complications. But over short periods of time, the air resistance can be kept to a minimum effect if we're using dense objects of pretty good size. Okay, and so that's it. So what if instead of dropping, what if we throw the ball downwards and we give it an initial velocity? We give it a v naught. So the v naught's not going to be 0 if we throw it. If we throw it, we have to put v naught is equal to 3 meters per second. And then it's saying after 1 second and 2 seconds, kind of the same questions here. And then compare it with just dropping. So here we go. The formulas I want to use now, here is velocity as a function of time, position as a function of time. The v naughts stay because now the v naughts are 3 meters per second. The x naughts are still gone. The x naughts are still 0. So those I don't have to keep around. But the v naughts do stay. So v is in the downwards direction, a is in the downwards direction, x is in the downwards direction. Everything is going to be positive. Everything that I calculate had better come out to be a positive number. And so t, I'm putting in 1, 2, 3 seconds, just the same as before. And this time, though, the velocities start out at 3, and so they're larger at each step in time. The velocities are 3 meters per second higher than they would have been if we hadn't thrown it down. So what effect does throwing it down have? Well, it gets an extra boost of 3 meters per second throughout the entire drop. So it's dropping with an additional 3 meters per second at each one of the times that we've measured. And that's going to have an effect on x. So x now has this extra term in it. So depending on how many seconds this drops, if this is an extra 3 meters per second and it drops for 3 seconds, that's going to give us an extra 9 meters per second. So let's try that. Here are the values that we get with the 3 meters per second in place. We can compare those. This is without the additional 3 meters per second in place. And you can see consistently, well, we're picking up that extra value of v naught times t. So after 1 second, that gives us an additional 3 meters that we've traveled. After 2 seconds, it's an additional 6 meters. And then after 3 seconds, it's an additional 9. So every second that goes by, we have traveled 3 meters farther than we would have if we didn't have that starting velocity. So throwing it down provides a consistent addition throughout the entire time that the object is dropping. All right. Freely falling objects. Here's another example. So we're starting here. Now this is kind of interesting. I'm not sure how this thing is being thrown, but it is. So what we're going to do is we're going to throw this object. There it is heading upwards. Now its velocity is in this direction, but the acceleration is downwards. Now since the acceleration we're treating as exclusively due to gravity, to represent the gravitational field, we use a little g. Now the little g gets called gravitational acceleration, but more strictly the gravitational field is what we're representing here. So the acceleration is equal to the field if there are no other forces being applied to the objects. So we're going to throw this object from point A. It rises all the way to point B, right where the velocity is 0, and then it comes back down. And when it comes back down, it's going to drop back, and the person's going to catch it, I guess, at the very same height. So what we've got is a complete trajectory up and a complete trajectory down. Now, what's going to happen to velocities and these little vectors that we've drawn here? So this velocity starts out large, and then it continues to get smaller as we go up. So they've only drawn one of these, but the velocity vector, the little arrow representing the velocity, gets shorter and shorter. Right at the top, it disappears. It goes to 0. And we saw this in the last lecture where we could graph this and show how the velocity is just decreasing steadily. And then starting from the top, now the velocity is going to be downwards and it's going to get larger and larger. So these arrows are going to get bigger and bigger on the way down. Now that's what's happening with velocity. The velocity is steadily changing throughout the entire trajectory. But what's happening with the acceleration? Well, the acceleration is downwards the whole time. All the way up, the acceleration maintains a constant value and it's pointed downward. So it's 9.80 meters per second squared in a downwards direction. Now in fact, we actually use the symbol little g to represent that gravitational acceleration effect. So little g is 9.80 meters per second squared, and it's defined as a positive number. So depending on how we set up our coordinate systems, the acceleration could be positive g or negative g. We'll see how that works in these examples. So they want us to come up with, if we throw this into the air at 15 meters per second, now that's going to be, what, 30 miles an hour or something like that, 35 miles an hour. Is that right? So we're throwing it at a pretty good speed. We want to know how high it's going to go, how long it's going to stay in the air before it comes back down. Now, I would suggest we break this into two parts. So there's a trajectory on the way up and there's a trajectory on the way down. We could treat it as one problem, or we could treat it as we could solve for everything on the way up and then solve for everything on the way down. And either approach should work here. So let's see what we've done here. So when I've thrown this upward, first of all, we're going to call this the positive direction, okay, or the positive direction. It's going to be the positive direction in this way. So x is in this direction, that's going to be positive. V is in this direction, at least on the way up. So it's going to be positive. And then for the acceleration is going to be downwards. So I'm going to write the acceleration as minus g, where little g is the gravitational field, which is creating a gravitational acceleration. And so that's 9.80 meters per second squared. We can actually write the gravitational field in the same units as acceleration. So it has acceleration units to it. All right, so at point A, we're starting off, let's call that 0 meters. That will drop out the x naught. Now the v naught is certainly not 0. So I'm starting off with an initial velocity. So, and then sometimes students will say, well, wait, doesn't the object just start at 0 and then you throw it? And the problem that we're working with right here doesn't address the time when the ball is being thrown. It only kicks in once we've let go of the ball. So the free fall doesn't begin until we let go. So the idea is we get the ball, we wind up, we throw it very forcefully, and then we let go. At the point where we let go, we're going to call that 0 meters, and at that point it's traveling 15 meters per second. I've let go of it. I no longer am going to have any effect on it. I gave it an initial velocity, now it's on its own, it's got to head out, it's got to fend for itself out in the world. But I gave it an initial velocity to start from. Now at the top, x is going to be some number, and that's actually what we want to solve for. At the top, another thing that we know is at the top of the trajectory, the velocity will have dropped all the way to 0. Now that's important. I have to have some way of knowing when I've reached the top, and setting v equal to 0 does that. So what I did was I pulled out equation number 3. I pulled out the equation that tells us about how velocities are related to displacements. And I said, it didn't ask about time yet. And so I'm just going to use this equation, and v squared is equal to v naught squared plus 2a x minus x naught. So that's the equation that we're going to be working from with this. Now the v is equal to 0, so that goes away. The v naught is 15 meters per second. That's going to stay. The acceleration that I put in needs to be minus 9.8 meters per second squared. So I am going to keep that as a. I could have put negative g in. And then the x naught is 0. So I dropped out the things that were 0. And I'm left with these terms, and then from that I can solve for x. X is then equal to negative v naught squared over 2a. Now the minus sign in the numerator will be canceled by the sign on the acceleration. The acceleration is in the negative direction. Okay, and so when I solve for the entire problem here, I'm going to have x is equal to 11.5 meters. That's the height that it reaches. So 11.5 meters, that's got to be like 35 feet, something like that. 35 feet high. So 3 meters, before we said that 3 or 4 meters, 3 meters is equivalent to about 1 story in a building. So this is going to be the height of a 4-story building, right? So if you think of a building, 1, 2, 3, 4, That's about how high this is, and then when we threw it at 15 meters per second, which we said is probably about maybe 30 meters per second, 30, not meters, 30 miles an hour. So just to build some familiarity with what these speeds are like. So 15 meters per second, 11.5 meters in height. Now, going from point A to point B, how much time did that take? So the time on the way up could be calculated by using V equals V naught plus AT, because we know that the V is going to be 0, the V naught is going to be 15, and the acceleration is minus 9.8 meters per second. So checking the units here, meters cancel meters, 1 of the seconds cancels 1 of the seconds, and then we are left with a seconds in the denominator of a denominator, and if something's in the denominator of a denominator, it's in the numerator, right? So when we take these units and multiply by their inverse, the seconds come upstairs. So we'll be left with units of seconds. The units match up, the signs canceled out successfully, we're getting a positive value for time, and the specific value of that is 1.53 seconds. Okay, so 1.53 seconds is how much time we're expecting for it to go up. What about coming from B down to C? Well, in this case, I can flip the coordinate system around again. If I want to start at B and come down to C, let's do this. Let's say now that x naught is equal to 0 and v naught is equal to 0 because it's dropping. That removes those two terms. That leaves us with x is 1/2 at squared. Now, since we're defining downwards as positive now, that means that the acceleration is now positive 9.80 meters per second squared. So plugging everything into that formula, I get the same answer. I get 1.53. It turns out that with constant accelerations, the time it takes to go up and the time it takes to come back down, it's going to be the same. Okay, we're kind of retracing our steps on the way. So I guess it doesn't have to be constant acceleration for this. It just has to be that on the way up, whatever the set of acceleration values were at each point we passed, at each time, it has to be duplicated on the way back down, and that's going to work. So that's a handy thing to keep track of, because when we solve problems now, as long as we go up to a height and we come back down to the same starting point, we can just say the times are going to match. If we took a video of this and then played it backwards, we wouldn't be able to tell the forward direction and the backwards direction with playing that video. Okay, this is not something that looks different when we reverse the order of time. Okay, so anyway, we switched the definition of our positive direction. Everything there is positive, and the times worked out to be the same. Okay, so good example of looking at these gravitational problems. Let's see, we've got freely falling objects. It says here that there's two common misconceptions, and I agree with this. So this is something we should talk about here. First of all, there's this idea that acceleration and velocity are always in the same direction. No, they don't have to be. Anytime something is slowing down, the direction of the acceleration is reversed. So anytime we're slowing down, we're going to have an acceleration in an opposite direction. So they don't have to be in the same direction. In fact, we're going to see cases where they're perpendicular to each other. So you can have any direction of acceleration with any direction of velocity. And then the second misconception is that when you hit the top of a trajectory, that the acceleration drops to 0, not even for a moment. Now, the velocity goes to 0 momentarily, but the acceleration doesn't. And we looked at graphs earlier describing that. So we've kind of looked at this. Okay, here's a follow-up example. We've got everything set up as before. The accelerations are pointing down consistently. Velocities are upwards on the way up and downwards on the way down. So it says this time, how much time does it take for the ball to reach the maximum height, and what's the velocity of the ball when it returns to point C? We may have already calculated some of these. I think we did. So I think what we can do is we can go back to the stuff that we looked at before. So what's going to happen here then is it took the same amount of time to go up and come down. And what's going to happen also as a result of the consistent acceleration effect is that by the time it comes back down, it'll be going to 15 meters per second that we talked about. Okay, so I think these have already been addressed. All right, let's take a look at this. Oh, we're going to look at this anyway. We're going to look at it in more detail. So here's the ball thrown upwards, and what we're going to end up, it says it's a quadratic formula, so let's see what that refers to. This is the height, which they're calling y, as a function of t. Now remember, at 1.53 seconds, we reached our top height, and that was at 11.5 meters. Now, the formula was a parabola in terms y as a function of t. It doesn't say the shape of the trajectory was a parabola. The trajectory itself, the ball just went straight up and straight down, and that's because we're only working in one dimension. We got to move on to chapter 3 before we see examples of more than one dimension. So the ball itself goes straight up and comes straight back down. But what we're graphing is y as a function of t, and that will have the shape of a parabola. It says calculate the times at which the ball crosses the 8-meter mark. So we can do that. We can go back and find out what times these occur at. Here are the results they got. We'll check and see if we get the same numbers or not. And then for the velocity as a function, so this is the graph that we had done before. We started off at 15 meters per second, going upwards in the positive direction. And then that number just decreased all the way to 0. And then as it continues, all the way to, what does this become, 3.06, I guess. 3.06 seconds have gone by. It will reach 15 meters per second in the opposite direction. So the velocity just steady, that slope just stays steady. And so right here, the slope is still 9.8 meters per second squared. The acceleration just stays constant all the way through. That's what v versus t is going to look like. Okay, so let's take a look at this question of at what times. Oh, look, I used y. So I decided to go ahead and use y for this vertical motion. That's fine. Y naught is equal to 0. So we're going to start with at the lowest position. And then v naught is 15 meters per second, and that's straight up. Now, they talked about how much time, so we're solving this for t, when y is equal to 8. So I can set y equal to 8, and then go in and solve for time. Now, g, I'm using little g. Little g is 9.80 meters per second squared, and I can plug that in. I put the minus sign in by hand. So to make sure that the acceleration is in a downwards direction, I put in g. G is defined as a positive quantity, so I've got to put a minus sign in there to make sure that we're keeping track of the correct directions. Now, this becomes a quadratic formula. So what's happening now is I have a term that has t squared in it, but I also have a term that has t in it, and well, y naught was equal to 0, that drops out, but I have a value of y. So I rewrote that equation right here in kind of standard quadratic form, and then I use the quadratic formula. So the quadratic formula says b over 2a plus or minus b squared minus 4ac divided by 2a, and that's what it looks like. Now, when you learn the quadratic formula, they tend to put everything over 2a. I think it's actually more useful to separate it into two distinct terms. So I do the b over 2a plus or minus b squared minus 4ac square root over 2a again. The reason for that is that often this term by itself means something in physics. So in this particular case, the v over g gives me 15 meters over 9.8 meters per second squared. That actually gives me the, let's go back and see. What the quadratic formula is going to do is going to give me two solutions, evenly spaced between a number in the middle. So if I'm looking at the times when it crosses the 8-meter height, one of those times is a little bit less than 1.53 seconds, and the other one is going to be a little bit more by the same amount. So there are plus and minus solutions here, and the quadratic formula set up this way takes care of it. What this is this number plus or minus this number here. Now when I solve those, what I found was my quadratic told me that the times at which the object crosses the 8-meter height is at 1.53 seconds plus or minus 0.84. So I like setting up the quadratic this way because I'm looking for meaning in each of these parts of the solution. This is the midpoint between the two solutions, and for throwing something up in the air, that's the time at which it's the highest height. Okay, anyway, we've solved for T1 and T2, those are the two solutions, and it looks like we got the numbers they got. So I think they did okay. They seem to have done fine on the problem. All right, more freely falling objects here. And so here is a ball thrown upwards from the edge of a cliff. Now I think before we threw one downwards, right? This time we're going to throw it up. Now conceptually, what's going to happen here? Let's see. So if instead of throwing it down, I throw it up, it's going to stay in the air longer, right? If I throw it upwards. But what's going to happen is, let's see, how fast do we throw it up in the air? Do they say? Yeah, 15 meters per second. Okay, so they've used that number before. So this is going to go up the 11 point whatever meters, and then it's going to come back down. How fast will it be traveling when it gets to right here? And you go, oh, we've solved that problem. If you throw it up at 15 meters per second, and we neglect air resistance, if air resistance is negligible, on the way down, it's going to be going downwards at 15 meters per second, and so it's going to land at the same speed. Again, neglecting air resistance, then this is going to be traveling at the same speed downwards when it gets to here, so it's the very same as if we threw it down. Now it does stay in the air longer because of that. Let's see, what else have they done? Oh, so they've set up an interesting coordinate system here. They've decided to go ahead and call this y equals 0 and let this be y equals negative 50. So that's a creative use of a coordinate system. They did not have to say this was at 0 and this was at 50. They decided to say this is at 50 and that's at negative 50. So that matches up. The cliff is 50 meters high. We need to find the time, the total distance traveled, and the and ignore air resistance. So air resistance we can we don't have to worry about. So we're going to throw it from a cliff. I'm trying out new variables here. I'm going to call this h. H is the height of my cliff. It's 50 meters. Now, for going from point A to point B, the time required for that, okay, this is kind of sideways across the board. So I've got this formula. We could have used this formula for the whole thing. I went ahead and did it in 2 steps. So a to b, y naught is equal to 0. V naught is equal to 15 meters per second. V is equal to 0. So when we solve for that and plug those numbers in, it's our 1.53 seconds back again. So it's that same example as before. So we're at 1.53 seconds. That's the amount of time to get from A to B. Now, how long is it going to take to go from B to C? Now, going to B to C, the starting point, I'm going to say at the top, I'm going to call that y naught equals 0. And then at the bottom is, it's going to be the 50 meters plus the additional 11.5 meters that we had solved earlier for the height. So we had solved the height, this will rise as 11.5 meters. So I'm adding those two numbers together and then following my formulas for displacement as a function of time, solving for time, I ended up with 3.54 seconds. So 1.53 seconds on the way from A to B, and 3.54 seconds from B to C. I can now add those two numbers together. So you can see that's another example of my tendency is to reset the coordinate system for different parts of the problem, and then at the end, add the numbers together. So this was the time from A to B, this is the time B to C, that's the total time. Okay, questions on any of that? Okay, let me know if there's questions on these. Now, as far as distances, so it said how far has the object traveled. Now, this we had also done. We had solved the distance going from A to B with a 15 meter per second initial speed. I'm back using the same formula. I'm getting the same results, the same numbers in the same formula. So from A to B, the object traveled 11.5 meters. And then for B to C, well, it's going to have to come back down the 11.5 meters and an additional 50 meters. That was given. So on the way from B down to C, that's going to be 61.5. Total distance traveled is 73.0 meters. Okay, again, it's an example of breaking a problem up into two separate parts, solving separately for the distances, and then bringing those numbers together. Okay, it's a good way to try it both ways. You know, try doing it in one fell swoop, where you just put one formula connecting points A and C, and then go back and break it up into separate parts and see if you can get the individual parts of the problem. See if you can get that to match up. So it should be doable. Now, as far as getting distance, I think for distance we've got to do this in 2 steps because our formulas are not keeping track of distance, they're keeping track of displacement. So if I try measuring displacements between A and C, I'm not going to get to 73 meters, I'm going to get 50. So for distance calculations, total distance up and plus down, we need to break it into two parts. All right, so we've looked at chapter 2 in a lot of detail. I always worry about this effect. I call it chapter fatigue, and that is when you start out a new chapter, everybody's enthusiastic. Those first few sections, everybody's reading, everybody's watching the lecture, they're taking notes. They're very enthusiastic. They're going to make everything in this chapter, they're going to make sure they understand it all. And then after, 8, 9, 10 sections, you get tired. And so you have to be careful with chapter fatigue. Now, here is a section near the end of chapter 2. Now, fortunately, this is not as important as the earlier section. Sometimes they slip important sections in at the end, and then you have to wake yourself back up. I'm not saying you can sleep through this one, but well, let's take a look at it and see. Usually what happens here is half the class says, oh, this is so cool, this is what we did in calculus last semester, and they're seeing an actual physics application and they're going, yes. And they get, very excited and they come up after and say, wow, that was exciting to see this out. And then the other half of the class comes up and says, do we have to know this for the midterm? And so, anyway, for both groups, let's go ahead and take a look at this. Here's an interesting idea that small differences in velocity can be related to accelerations times small time intervals. So, we said that when we take derivatives, such as this, we can actually treat dv and dt as variables. They just represent little pieces of time, little short intervals of time, and little short variations, small variations, infinitesimal variations in velocities. And so what we can do is we can separate it out like this, and then we can integrate both sides. Now, I'm not sure, the official rules are in Calculus 1, I believe, first semester calculus, that you do get to basic levels of integration. And then I know in the second semester of calculus, integration just goes crazy, right? So you're learning all of these substitution methods, and so I want to assure you that we're not going to get, we tend not to get out ahead of that, but if we do, if there is something that you need to know that maybe you haven't seen in your calculus classes yet, we're going to make sure that we look at that in some detail. So, and that's just what happens. I remember being in college, and there were times when I would learn some new technique in my math class first, and later in physics, but there were also times I would learn calculus tricks in physics, and then I would see them later in my math class. We just want to make sure that we're supporting those fully. All right, so there's our definition of acceleration, and we can rewrite it this way, and then we can integrate both sides. So what we're doing on the right side is we're letting little bits of time go by, and that's designated by the limits of integration. So we're going to start off at the time t equals 0, and then little bits of time go by, and we're going to keep track of the acceleration times those times. So that's keeping track of the acceleration. Now the acceleration might not be constant, right? So maybe it stays inside the integration. If it is constant, it comes outside the integral. So, but we're going to start with this as the general expression. Now on this side, what we're doing is saying, hey, every time a little bit of time goes by, and there's an acceleration going on, there's going to be a shift in velocity. And the left side is keeping track of all the changes in velocity that occur. So we have to make sure the limits match up. So if I start off at t equals 0, well, the velocity needs to start off at v0. And then we're going to let that extend out to some variable value of t. So we'll let this extend out to some variable value of v. But the v that we integrate on this side corresponds to the t that we integrate on the other side. So we've gone through a series of steps. We've added up all the velocity changes. We've added up all the time intervals. We've multiplied by the appropriate factors. That has to be true then, whatever we come up with. Now for constant acceleration, this side, when we integrate this side, it's going to become v minus v naught. This is a pretty straightforward integration. In fact, it's so straightforward, it's almost a little confusing that there's nothing in here but the dv, but when I integrate dv, I just get v. And v evaluated between v naught and v gives us v minus v naught. Now this side, if the a is constant, comes outside, and then when I carry out the integration, it's just t. So for constant acceleration, this is pretty straightforward. What we can do then is we can move on to our next step. We can say v is equal to dx dt, and then separate that out and say dx is equal to v times dt. Now, what we did on the previous slide is show that if the acceleration is constant, then v is equal to v naught plus at. So we slip that into the integration. And now when we draw the integral signs, we integrate from x naught to x, we integrate from 0 to t. This side is going to integrate out to x minus x naught. This side is going to integrate out to v naught times t. This at term is going to integrate to 1/2 at squared. So what we've done here is we've re-derived our formulas for constant acceleration. So we've re-derived our formulas for constant acceleration, and we've done that using official integral calculus and official derivative definitions, infinitesimal definitions of velocity and acceleration. Okay, so that's good to know that we can come back and derive those, I'm going to say a little more thoroughly using calculus. Now let's try an example of this. I think we have time to slip in this last example. So what would happen if the acceleration were not constant? So what it's saying is that we have an experimental vehicle, starts from rest, so v naught is equal to 0 at t equals 0. It accelerates not constantly, but the acceleration is increasing with time. So that says that the acceleration starts out to be 0, but after 1 second it's gone up to 7 meters per second cubed. And that's not the acceleration though, huh? You have to multiply by time. So with 1 second here, that would be, the seconds cancel. So 7 meters per second per second. The one factor of seconds in time will cancel one of these factors. Always these constants out in front. You always have to take a close look and make sure you understand the units in those. What's its displacement? So let's take a look at this. So here is our experimental vehicle. It looks like a car. It's going to go in that direction. It's going to accelerate in that direction. It's going to start off at 0. I'm going to write this as a is equal to a times t. A is equal to 7 meters per second cubed. Now I wrote this as dv equals a dt. Same thing as what we talked about before. I set up the integral. But notice this time when I take the integration, there's an extra factor of t right there, and that stays in the integration. So v now is not directly proportional to t. V is not going to be increasing linearly. It's going to be increasing like t squared. Now I can do one more integration. What I can do is say dx dt, which is velocity, is 1/2 at squared. And then I can do the second integration, and the displacement, when I carry out the integration, I now have t squared inside the integral, and integrating t squared becomes 1/3 t cubed. So that gives me, I got a factor of 1/3 here, a factor of 1/2 here. That gives me x is equal to 1/6 a t cubed. So at 2 seconds, the velocity is 14 meters per second by plugging into my velocity formula. And the distance that, the displacement will be 9.3 meters. Okay, so it's an interesting example. I don't know if you see anything like this in your calculus classes. Just checking time here. Looks like we have a few more minutes. I don't know if you see anything like this in your calculus classes, but this is a more general way to come up with formulas for velocity and displacement. So summary of chapter 2, you guys should congratulate yourselves. This was a lot of detail that we looked at. I hope that worked well. Again, make sure that you are staying up. We looked at chapter 2 in great detail, and that means that we're going to be really well prepared looking at the next chapter. Chapter 3 is going to be a continuation of looking at kinematics. Only we're going to now move on to looking at 2- and 3-dimensional motion. All right, any questions at all? Stop by office hours. Let's get those questions looked at.